Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on reflection photoelasticity. I said this technique has been really used for solving several problems of practical interest. The methodology requires use of correction factors, because I mentioned we make several approximations in the theoretical development, and also in optical arrangement we compromise on pure normal incidence. A small angle of oblique comes into the picture, and I also said that this is applicable for a variety of materials ranging from rubber to bone to composites to high strength alloys. So, the range and versatility, these are the two key factors, and even now for some of the current problems people employ and go to photoelastic coating and find out how to get the pertinent information for design. And mind you, whoever does original design, they need all these experimental methods. If somebody copies the design, he does not require anything. When you are making your own design, you need to verify whether whatever the kind of procedures that you have adopted has come and be useful for arriving at a right kind of design for a given problem. And we will look at what are the correction factors we looked at, and this is more of a summary. Depending on the type of problem, whether it is plane stress, beam in bending, or bending of thin or medium thick plates, and torsion of circular shaft, you have the correction factors available here, and we have this as RFA, where A denotes that you are looking at axial loading, and this is labeled as RFB, B denotes bending, and this is RFBP to distinguish from bending of beams to bending of plates. You have this as BP, and RFT is used for torsion. And in all these expressions, in order to simplify your writing, we have used E as ratio of Young's modulus, and G as ratio of thickness, and M as 1 minus nu S squared divided by 1 minus nu C squared. And I said that you also have the correction factor for pressure vessels, because many engineering applications could be modeled as a pressure vessel, and here it is written as 1 by RFP, and you also have the definition of A and C, and you also have a definition of what is the symbol P used in this expression. And you have to understand these correction factors are applicable in regions away from stress concentration. When there is abrupt changes in the thickness, then also these correction factors are not valid. The idea here is, when you have a real problem on hand, apply a coating of reasonable thickness, so that you find out which are all the regions you have high stress gradients. Identify those regions, then strip this thick coating and then put a thin coating. So, you avoid the use of correction factors in stress concentration zones, because if coating is thin enough, then correction factor importance also diminished. So, that is a way you circumvent. When you have to analyze complex problems, you have an engineering approach to utilizing the technique. And when you look at the correction factor for long cylinder pressure vessel, they are very important when you are looking at tubing, not for large pressure vessels. You have heat exchangers where you have tubing, and for these tubes people have analyzed, and particularly in nuclear industry you have to be very careful. So, high pressure tubing, the use of correction factors are very important. I also mentioned that you need to look at how to handle mismatch of Poisson's ratio. That is what we will take it up now, and let us understand the mismatch of Poisson's ratio. How does this affect? So, what is shown here is I have a simple specimen subjected to uniaxial tension. I take axis 1 along the specimen, I take axis 2 transverse to the specimen, and I have a photoelastic coating pasted on this. And if you take a section here, I show the section will look something like this. It is deliberately shown that you have this coating interior, it is not extended to the full length to illustrate the point. And what happens when I apply a longitudinal load, the strain in that direction is completely governed by the load applied. And I have always been saying, when you are dealing with strain, you should understand that stress is uniaxial, but strain in general is biaxial or triaxial depending on the kind of specimen that you are looking at. If you want to have uniaxial strain, then you have to make special efforts to constrain the edges appropriately. Uniaxial stress is simple, uniaxial strain is not simple. And what you should look at here is, I have applied a uniaxial loading, stress is uniaxial, but strain is biaxial. So, the longitudinal strain is governed by the applied load, whereas the lateral strain is a function of both the load applied and the Poisson's ratio of the specimen. So, what I have here is epsilon 1 c equal to epsilon 1 s, there is no problem, and we have epsilon 2 c is also equal to epsilon 2 s, because we assume that the bonding of the coating is very carefully done, so that whatever the strains developed in the specimen are faithfully transmitted to the coating. If the coating is very thin, then you do not have much of a problem, and we are talking about a finite thickness coating. So, I can think of a surface which is bonded to the specimen and a surface which is free. The top surface of the coating is free. So, if you look at what happens at the bonded surface, then epsilon 2 s is actually minus nu s times epsilon 1 s, and this will be equal to the coating strain, no problem. But what happens on the top surface? On the top surface, the strain is related to nu c times epsilon 1 s. So, this is the difference. See, these are all second order effects. When you are developing a methodology, before we neglect certain aspects, we should also analyze and find out what is its influence. After your analysis, you find that influence is small enough, then you can label it as second order effects and then carry on with your analysis. So, in order to appreciate what happens when there is a mismatch of Poisson's ratio, what we find is there could be a strain variation through the thickness of the coating, because you have a surface bonded to the specimen where you will have only nu s, but when the surface is free on the other end of the thickness, it is governed by the Poisson's ratio of the coating. See, we saw in the case of coating applied to bending problems or torsion problems, there was a variation in the coating, the strain variation in the coating was seen mainly because of the way the model was loaded, model or the prototype was loaded, you had a strain variation, that is acceptable. But you can also have a small variation of strain through the thickness if there is a mismatch of Poisson's ratio. This is one aspect of it. The other aspect is when I have free edges, there also you have to bring in the Poisson's ratio of the coating in your analysis. And people have done studies and then looked at what way one has to consider this, in which region Poisson's ratio is important, and for all this we have also seen from the material property that Poisson ratio of the photoelastic material are in general larger than the specimen material, if you are looking at metallic specimens. And what you have is the fringe order n observable lies in the range, straightforward application of your strain optic law. I do not know how many of you are able to see this. I will have epsilon 1 minus epsilon 2 as n f epsilon by 2 h c, and this epsilon 1 minus epsilon 2 is written in this fashion here, because I know epsilon 1 s minus of minus nu s epsilon 1 s, because epsilon 2 s is minus nu s epsilon 1 s. So, in one case it may be controlled by the Poisson ratio of the specimen, in another case it can be controlled by the Poisson ratio of the coating. So, the n will have a range on the one end dictated by the Poisson ratio of the specimen, on the other hand it is dictated by the Poisson ratio of the coating. So, you define what is a boundary fringe order, it is given as 2 h c into 1 plus nu c into epsilon 1 s divided by f epsilon, and I can also write what is the interior fringe order, it is given as 2 h c into 1 plus nu s epsilon 1 s divided by f epsilon. This is the material strain fringe value. So, what you need to recognize is Poisson's ratio mismatch can give problems, whether the problem is significant or not is what you will have to look at, and people have also done systematic experiments and then established how you can accommodate the Poisson's ratio mismatch. So, what we have looked at earlier was you had fringe orders different at the boundary and the interior. When you have a difference, there has to be a transition zone. So, people have identified a transition zone exists near the boundary where the fringe order lies between the two extremes which we saw earlier, and this can be expressed as n transition, and that is given as 2 h c into 1 plus nu s plus C v, where C v is the correction factor accounting for the mismatch, C v multiplied by nu c minus nu s, the whole of it multiplied by epsilon 1 s divided by f epsilon. And this is what I said, that experiments have been conducted by researchers, and if you want to study the influence of Poisson's ratio, the best kind of specimen you can think of is composites, because when I have a composite, I can change the volume fraction of the fiber, by which I can change the Poisson ratio of the composite specimen comfortably. and this is what was done. So, the glass fiber epoxy tension specimens where the specimen Poisson's ratio is varied between 0.097 to 0.35. When you use a composite, by changing the volume fraction of the fiber, it is possible to change the Poisson's ratio, and further details you could get it from reference here. It is by Daly and Alferwich, it was published in 1969. You have application of birefringent coatings to glass fiber reinforced plastics. In fact, you have very nice pictures, and they have also given thumb rules depending on the coating thickness, what is the size of the transition zone, and so on and so forth. And what is its implication when we want to do experiments? And this is what you see here. And what they have found is, for a fixed coating Poisson's ratio of 0.36, which is reasonable to assume, the boundary fringe order is always found to be higher than the interior. That is mainly because of the Poisson's ratio mismatch, and the length of the transition zone is found to be 4 times the thickness of the coating. So, this is the contribution by the experiments conducted by Daly and Alferwich. They have also established the size of the transition zone, it is a function of the coating thickness. And what you actually have to look at is, what is the change in the Poisson's ratio. You know metallic specimens, the Poisson's ratio is around 0.26, 0.24 to 0.26 is what you have. So, typically the Poisson's ratio difference nu c minus nu s is usually less than 0.06. So, the final conclusion is, for most metallic components, the effect of Poisson's ratio mismatch is often neglected. That is a saving grace, because before we establish that this is a second order effect, we must do an analysis and then only say Poisson's ratio mismatch can give you problems, but the level of influence is smaller. So, you can neglect it for metallic specimens when you do photoelastic coating testing analysis. However, when we go and do the SCF evaluation, that is what I said, when I want to find out the stress concentration factor, photoelasticity is a very simple approach to find out stress concentration factor. And what we need in transmission photoelasticity is, you need to find out n max and n far field, and their ratio directly gives you the stress concentration factor. But in view of the Poisson's ratio mismatch, you have to modify this expression slightly. So, that is what you see here. So, stress concentration factor, if I use photoelastic coatings, you have to have n max divided by n far field, which is multiplied by 1 plus nu s divided by 1 plus nu c. So, the Poisson ratio of the specimen as well as Poisson ratio of the coating influences your final result. So, if you do not do this correction, if you have a finite element analysis and evaluate the stress concentration factor, it will not match, because essentially you are going to find out SCF for finite body problems. For all finite body problems, either you have to depend on a numerical approach or an experimental approach. Analytical approach, you will have stress concentration factor only for an infinite geometry. Do not think for all holes stress concentration factor is 3. That was developed in theory of elasticity for an infinite plate with a small hole. When you go to actual problems, you have a finite plate with a finite sized holes. In general, stress concentration factors are much higher than 3, and there is also a subtle difference. In the case of theory of elasticity, you define stress concentration factor as maximum stress divided by far field stress. That will be 3 for an infinite plate with a small hole. For a finite plate, it will be greater than 3. But if you go and look at design codes, they are defining stress concentration factor slightly differently. They would define stress concentration factor as maximum stress divided by the ligament stress, because that is what you can estimate for a finite body comfortably. And when the size of the holes keeps increasing, the ligament stress also will keep increasing. So, what you will essentially find is stress concentration factor will hover around 2, 2.2, 2.3 and so on. You should not wrongly conclude theory of elasticity gives me 3, whereas design books gives me less than 3. So, I can always use 3 as the conservative value for my design, then your design will fail, because many people do not know. This is a subtle difference. There is a definition shift between designers, how they define stress concentration factor, and how do you define stress concentration factor in analytical development. You should know the difference. Half baked knowledge can always give you problem. So, you have to be very careful when you want to find out SCF in photoelastic coatings. You should also put this correction factor. This comes from mismatch of Poisson's ratio. And what should be the property of ideal photoelastic coating should have? Obviously, we want to have high strain coefficient K. The reason is I need to get enough optical response, and we have also seen if the coating is thin enough, I do not have to worry about the correction factor, which is automatically taken care of. Only when the coating thickness is considerable, then correction factors are very important. So, from that point of view, you want to have high strain coefficient K, and the reason is small coating thickness is sufficient to give enough optical information. And you want to have low Young's modulus, because you do not want this to reinforce the specimen, and you want to have a linear stress strain and strain fringe relations, so that interpretation becomes lot more simpler. Easy bondability to various specimen materials, because we had seen earlier people used glass, it was difficult to bond, and it should also have capacity for good machinability, and particularly when I want to go for complex industrial components, the coating material should have pliability for me to form the shell of the actual object. In fact, I would try to show you some practical examples that has been reported in the literature to give you a flavor how this methodology is relevant even today for solving complex problems. That will also give you a motivation that to learn this technique, and also if opportunity exists for you to apply. And obviously, you will not have all these properties available in a single material. So, you have to have a trade off and you have to do compromises. These are all the desirable requirements. And what you have is, I said that the Young's modulus is a very key factor, because we do not want this to reinforce the specimen. So, you have coatings available separately for high modulus materials, and if you look at the Young's modulus, it is around 3 GPa, whereas all your materials, when you have metallic materials, they have aluminum is 70 GPa, and steel is 210 GPa. So, if you have a coating which is just 3 GPa, it will not reinforce that. So, I can comfortably use photoelastic coating, and from this table you write only two material, one is polycarbonate, another is PS1. This is also commercially available from Vishay Micro Measurements, and what you need to look at is K is around 0.16, 0.1 is what you see by and large for most of the materials, and strain limit is it can go up to 10% of strain, and because these are all plastics you can't go beyond maximum of 260 degrees centigrade, and you also have whether they can be available in flat sheet or contourable form. When you have a contourable form, you essentially have a liquid and you cast it in your own laboratory, or I also said that with advancement in technology, people also give you the sheets in gel state properly preserved with dry ice, and it is available for a high price. So, you could also get them, but that is contourable, and this is needed for complex industrial components. And what you need to look at here is for high modulus materials, the recommended coating have Young's modulus around 3 GPa, and Poisson ratio is around 0.36, that is how all the materials that you have, and most metallic materials it will hover between 0.24 to 0.26 or 0.28. So, this is how you have to look at the relevance of these numbers. And when I go to low modulus materials, and I have for medium modulus materials separately, and I have low modulus materials finally like rubber. So, you have special materials available from Vishay Micro Measurements, which is available at a Young's modulus of 0.21 GPa, and you have strain limit of about 30%, and if you look at K for this, it is considerably reduced 0.02. Finally, when you come to rubber, and here you have to be very careful. See, you think rubber does it require any analysis? In fact, if you look at tires which are used in aircrafts, very complex design. They are like layered composite, you have reinforcements, and during landing and takeoff, tires play a very important role, and they have to withstand the entire weight and impact loads, and tire design is very complex. Do not think because you use your tires in your cycles, and then you also use in many of your common day to day applications, many times familiarity brings as if you know everything about it. In fact, tire design is very complex from material modeling point of view, from fabrication point of view, and also from analysis point of view. So, you need to analyze rubber also. So, in tire applications, you have to be careful in selecting a suitable coating. So, what you have here is it is a low modulus material, and I choose a coating which has a very small Young's modulus, it is 0.004 GPa, polyurethane, PS4, and when you look at strain limits, because rubber you know it can have a very large strain. So, these are available greater than 50%, applicable even for greater than 50%, and you have flat and contourable type of classification. So, what you need to keep in mind is for different type of specimen materials, you have variety of coatings available, and you have to pick and choose. See, if I use a high modulus material coating to a low modulus material, then I would be making a mistake, because the coating will reinforce the specimen. So, what you will have to be careful is you need to choose the appropriate material. So, you have a catalog available, utilize the catalog properly. And I also mentioned there is an issue of selection of coating thickness. Ideally, I want the coating thickness should be as small as possible. We said we want to have a very high value of K, then I can have coating thickness as small as possible. And we also want to have the chosen coating thickness should be sufficient to produce a meaningful number of fringes for easy measurement. And we have seen in transmission photoelasticity, by increasing the model thickness, I can increase the number of fringes. The same philosophy also applies here. So, if I do not have sufficient optical response, I cannot make measurement. So, in order to make measurement, I can increase the thickness of the coating, that is one method. The other point of approach is by increasing the applied load. Increasing the applied load, I cannot do it comfortably beyond a limit in the case of metallic components when I do an elastic stress analysis, because if I increase the load, the specimen may start yielding. You do not want the specimen to yield in normal service condition. So, there is an upper limit by which I can load it. So, one of the issue talked about in photoelastic coating analysis is what are the maximum fringe orders obtainable. It is an issue. That is why we look at what is the selection of coating thickness. We want to have a trade off between optical response and use of correction factors or reinforcement effect, and also look at what way the analysis influences it. I am essentially looking at the elastic stress analysis, and from the equations we can go back and find out what is the maximum fringe order obtainable, and that is what is given here. So, what you have here is essentially we are going to get sigma 1 s minus sigma 2 s, and suppose I consider that these principal stresses are of opposite sign, and suppose the material follows Tresca yield criteria, then for a yield strength Sy of the material, the maximum value of sigma 1 s minus sigma 2 s is only Sy. So, from this, if I go back and find out what is the expression for the principal stress difference, recast that expression. So, you have maximum fringe order obtainable is a function of Poisson ratio of the material, Young's modulus of the material, and also the yield strength of the material. So, what you find is if I am working on high strength alloys, I can have very high fringe orders. Low strength alloys, the maximum fringe order obtainable is smaller, and most of your aerospace and nuclear application you use high strength alloys. So, you will have reasonable fringe orders seen in those structures. Suppose I want to apply it on mild steel, that is also need to be analyzed. When you make a component out of mild steel, that also needs to be analyzed, you will not have very high fringe orders. So, that we can actually calculate for a given coating material for different specimen material, what is the maximum fringe order obtainable. So, I have this expression n max equal to 1 plus nu s divided by E s into 2 h c into k, that is a strain coefficient of the coating material, and you have the wavelength dependence, and you have this as Sy as the yield strength of the specimen material. And I also have a table which gives you for a variety of materials what is the fringe order obtainable, and what you have is we have taken a coating material of K equal to 0.15, and for a coating thickness of 1 millimeter, and for a light source of wavelength 577 nanometers, essentially the white light. We had also looked at the color code where we saw repetition occurs at 577 nanometers. You have a tint of passage, and twice of this value you have another tint of passage. And what you need to look at here is, I have the yield stress tabulated here, and yield strength is increasing, and for a HR 1020 steel, the maximum fringe order obtainable is only 0.78, whereas on a maraging steel it is about 5.58. So, if I am working on high strength alloys, it will be very similar to what I see in the case of transmission photoelasticity. I will see rich colors, but a thumb rule is, if you see rich colors, you have very high values of stress. You should never forget that. And in the case of common materials, the fringe orders obtainable are very small, and mind you, this is when the material specimen material yields, and we will never load in actual service condition to the extent of yielding. So, we will operate much below this. So, the message here is, when you go for photoelastic coating analysis, the specimen material indirectly influences what is the maximum fringe order that I can anticipate to observe in a test. And this also gives a knowledge that usually the fringe orders what you can perceive are smaller, and that is the reason why you want to go for white light for illumination. And I also have this table for some more materials. The idea is to have a picture. The same thing happens in the case of aluminum also. So, aluminum, it ranges from 1.37 to 4.88. People also have used photoelastic coating in concrete, and concrete the maximum fringe order is only 0.95. So, this gives you an indication that photoelastic coating, the fringes observable are very less. So, it is better you go for white light illumination. We have seen that the maximum fringe order obtainable is quite low for many materials. This necessitates the use of higher thickness coatings for better data reduction. And what happens if thicker coatings are employed, appropriate correction factors are needed for data reduction. So, you need thickness selection philosophies for you to address these issues. And what I have here, to simplify data reduction, I have also mentioned it earlier, while using flat sheets, it is generally recommended to determine the coating thickness such that the correction factor is unity. Whether keeping it unity helps your particular application or not, that needs to be verified, but this is one of the philosophies that one can think of, because the focus is to simplify data reduction. The other aspect is, in order to ensure that the change in correction factor is a minimum, the second derivative is to be computed and its sign checked, because what you want is, when there is a thickness change, this becomes important when you go for contourable plastic. You will not be in a position to maintain the thickness uniformly. So, there you would like to have a correction factor not to change drastically because of small variation in thicknesses. And that is what is summarized here. While using contourable plastics, it is difficult to maintain the thickness of the coating over the component surface. So, in such applications, the coating thickness should be found such that small variations in coating thickness do not unduly change the correction factor. In fact, we are going to see a variety of problems which are very complex in shape, where contourable plastics have been employed to analyze a variety of practical situations. So, in such cases the coating thickness should be found such that small variations in coating thickness do not unduly change the correction factor. And how do we do it? The first solution can be easily obtained by equating the solution, that is the correction factor, to unity, because the focus was to find out the thickness such that correction factor is equal to 1. In some applications you may find that thickness, but thickness may not be suitable, that decision also you have to take. So, the thickness selection does not end here, it only gives you a possible selection of thickness. What happens when RF is equal to unity? The second solution is obtained, that is the thickness should not change, the correction factor should not change for small variations in coating thickness, is obtained by differentiating the correction factor expression with respect to G, and we have already seen G as ratio of thicknesses. So, whatever the expression you have for correction factor, that needs to be differentiated with respect to G, and ensure that whatever the correction factor you get is not changing drastically for small changes in the thickness, because it is very difficult to maintain thickness for large structures, there could be small variations, and these are only philosophies, it is not the end result. As an engineer, you should apply your engineering acumen and filter out whether you will employ these kind of approaches. Finally, you always have what is the available thickness readily from manufacturers is also dictates the final selection. So, this is one of the considerations based on analysis, whether I want to have correction factor RF equal to 1 or change of correction factor should be minimum for changes in thicknesses. Now, if you look at the literature, there was a book by Zandman and others, it was a monograph published by Society of Experimental Mechanics, that was the only book available earlier on photoelastic coatings, that had nice pictures on some of the components that they had analyzed at that point in time. And recently the Vishay Micro Measurements has brought out a nice book on photo stress, and which says pictorial examples of photo stress coated parts, and it also gives wide selection of industrial case history applications. My interest is to enthuse you to take up photoelastic coating for your solving industrial problems. And if you look at the kind of problems that have been analyzed, that will give you an idea how to go about. The idea of showing this book is that it has a rich collection of examples where photo stress has been applied, and this has very interesting set of pictures. If you have an opportunity, please get hold of this book and read through it. My interest is to give you a appreciation that what variety and range the problems can be tackled using photoelastic coatings. This is an example which shows how photoelastic coating is useful for studying assembly stresses, and this is the mask that is used for the street lighting, and you have here it is tightened. After tightening with the bolt, it has developed rich colors indicating a very high value of stresses because of assembly. This shows another example of application of photoelastic coatings. Here you have a flywheel that is being analyzed. I had mentioned that when you see colors, you have to be worried in photoelastic coating test, that indicates the stress levels are very high, and this is the initial design of the flywheel, and these are the stresses due to assembly. Based on this input, when the design is modified, you have the final set of assembly fringe patterns, which are very good from design point of view. From photograph point of view, you do not see colors. From photogenic point of view, this figure is very good, but from design point of view, this is what we want, and this shows how photoelastic coating can be effectively utilized for studying the assembly stresses and also take corrective measures for improved design. This shows another example of what is the use of photoelastic coating in solving industrial problems. This is the model of a A330, A340 landing gear, and what you have here is, you can see the size of the model compared to the human being standing, and what is interesting is you have this as a epoxy model, that is very clearly seen from the color. You can see from the color that this is a model made of epoxy. In fact, chemical engineers are employed to tame the epoxy material, so that they get the model free of residual stresses when such a huge model is being cast. So, what you have here is, the figure clearly shows that this model is made of epoxy. You can distinguish it from its color. So, the entire model is made of epoxy, that is coated with photoelastic coating, and you can see the individual, the person watching for stress concentration using a reflection polariscope held in his hand. This shows another example of a component of a landing gear. This is a 767 main landing gear, how photoelastic coating reveals stress patterns for a problem of practical interest. This shows another example of application of photoelastic coating, and here it is for prosthesis example, where you have hip replacement and you want to analyze what is the influence of this implants. You have a shell which is made by contourable plastic, which is bonded onto the bone, and these are all the respective fringe patterns obtained for various configuration. So, you have a range, you have seen for metals, now you see for application of photoelastic coating to bone. Finally, you see application of photoelastic coating to the tire of a aircraft application, and you see the tire bonded with photoelastic coating, and these are all the fringe patterns observed. And mind you, here you have to use the appropriate coating material to reveal the stress pattern. See, what we have discussed in today's class was, we looked at that photoelastic coatings is industry friendly technique, and correction factors are part and parcel of it, because we make approximations in the optical arrangement, as well as when you are having a coating of reasonable thickness, you need to account for it, and in order to correct those kind of errors, you always bring in the correction factors. Then we also looked at what is the influence of mismatch of Poisson's ratio. We found out thumb rules, what is the size of the transition zone, and we also concluded that as long as I work on metallic specimens, we can ignore the influence of Poisson's ratio mismatch. However, for finding out stress concentration factor, it is desirable that you bring in a small correction, which is given as 1 plus nu s divided by 1 plus nu c. Then we moved on and looked at what are the different kind of photoelastic coating material, and I said you have coating material specifically available for high modulus specimen materials, medium modulus specimen materials, and low modulus specimen materials. Finally, we also looked at what is the maximum fringe order obtainable in a photoelastic coating test. And in order to give an enthusiasm that this technique is very widely used in industries which concentrate on design and development, like in aircraft industry and also other key industries where they generate original designs. We have seen a variety of problems where photoelastic coating has been applied even for some of the very recent aircrafts like Boeing 777 or 767 and also Airbus A380. People have used photoelastic coating to verify the design of landing gears. So, that should enthuse you to understand what is the method of photoelastic coating and also employ it when you have an opportunity to do any of those design development.